Hey everyone, welcome back. Today we're tackling LeetCode problem 416, partition equals subset sum. The goal sounds simple enough. Can we split a list of numbers into two groups that add up to the same value? Let's break down exactly what that means and how we can figure it out. So the problem gives us a list of positive numbers. We need to return if we can divide all these numbers into exactly two separate groups, where the sum of the numbers in the first group is equal to the sum of the numbers in the second group. If we can't make such a split, we return. The constraints tell us the list won't be too huge, maybe up to 200 numbers, and the numbers themselves aren't massive, up to 100. This gives us a hint about what kind of solutions might be efficient enough. Let's look at the first example. The numbers are 1, 5, 11, and 5. Can we split these? What if we put the 1, the first 5, and the second 5 together? That group sums to 1 plus 5 equals 11. What's left? Just the number 11, and that group sums to, well, 11. Hey, the sums match. 11 equals 11. So yes, we can partition this array equally. The output is true. Make sense? Okay, how about this one? 1, 2, 3, 5. Let's try grouping them. Maybe 1 and 5? That's 6. The leftovers are 2 and 3, which sum to 5. Nope, 6 is not 5. How about 1, 2, 3? That's 6. Leftover is 5. Still no match. Try 1 and 3? That's 4. Leftovers 2 and 5, sum to 7. No luck. It seems like no matter how we try to split these four numbers into two groups, the sums just don't end up being equal. So for this input, the answer is false. Okay, let's think about a fundamental property here. If we can split the list into two groups with the same sum, let's call that sum. Then the first group adds up to, and the second group also adds up to. What's the total sum of all the numbers in the original list? It has to be s plus s, which is 2 times s. This means the total sum must be an even number. If we calculate the total sum of the input list, and it's odd, we know immediately it's impossible to partition it into two equal sum subsets. That's a quick check we can do right at the start. So if the total sum is odd, we're done, it's false. But what if the total sum is even? Let's say the total sum is, if we can split it equally, each subset must sum up to exactly half of that, right? So the target sum for each subset is t/2. Now, think about this. If we can find just one subset of the original numbers that adds up precisely to this target underscore sum, which is t/2, what about the remaining numbers? Well, their sum must be the total sum minus the sum of the first subset, t/2, which is also t/2. So finding one subset that sums to half the total is enough proof. This transforms our problem into a classic one, the subset sum problem. How do we solve this subset sum problem? A common way is using dynamic programming. Let's imagine we have a way to keep track of all the possible sums we can create using the numbers we've looked at so far. We can use a Boolean array, let's call it dp. dp will be true if we can make a sum of exactly s using some combination of the numbers we've considered, and false otherwise. Our ultimate goal is to figure out if dp, target underscore sum, is true, where target underscore sum is half the total sum of the input array. Okay, so we need this dp array. How big should it be? Well, the maximum sum we care about is our target underscore sum, so the array needs to go from index 0 up to target underscore sum. We can initialize everything to false, except for one crucial spot. dp0 should be true. Why? Because you can always make a sum of 0 by picking no numbers at all, an empty subset. Now, we'll process each number in our input list nums, one by one. For each number, we'll use it to potentially update our dp array, finding new sums that become possible. Here's the key update step. When we consider a number, let's call it num, we need to think about how it helps us make new sums. We look at the sums s that we might want to achieve, starting from our target sum, and going down towards num. For each potential sum s, we ask, could we already make the sum s num, without using the current number num? If the answer is yes, meaning dp's num was already true, then by adding our current num, we can now definitely make the sum s. So we set dp to true. Now why iterate downwards from target to num? This is super important. Imagine we went upwards. If we found that dp5 became true because of num equals 3, since dp2 was true, and then later in the same pass for num equals 3, we check dp, we'd see dp to 3, which is dp5, is now true, but that dp5 only became true because we used the num equals 3 we're currently processing. That would be like using the same number twice. By iterating downwards, when we check dp's num, we are guaranteed to be looking at whether that sum was possible before considering the current num in this pass. This correctly simulates taking each number at most once. Alright, here's the Python code implementing this dynamic programming idea. First, we calculate the total sum and do that quick check. If it's odd, we immediately return false. If it's even, we calculate our target sum. Then, we initialize a way to track achievable sums. Here I'm using a set called possible_sums, starting with just 0. A Boolean array works just as well. We loop through each number in the input list. Inside, we figure out what new sums we can make by adding the current number to the sums we could already make. If any new sum hits our target exactly, we found our answer and can return true right away. Otherwise, we add these newly possible sums to our main set or update the Boolean array. If we go through all the numbers and never hit the target, it means it's impossible, so we return false. The commented lines show how you'd do it with a Boolean array and the downward iteration we discussed earlier. Both ways work. So how fast and memory hungry is this DP solution? Let's say is the number of items in our input list, and is the target sum we're aiming for, half the total sum. The time complexity is roughly n times s, big O of n times s. This is because we have an outer loop running times for each number, and the work inside, checking and updating possible sums, can, in the worst case, depend on how large the target sum is. The space complexity is determined by the size of our DP array or set, which needs to store information for sums up to so. The space is order s or big O of s. Given the problem constraints, n up to 200, max s around 10,000, this ns complexity should be perfectly acceptable. Okay, let's recap the main points. First, always check if the total sum of the numbers is odd. If it is, you can't possibly split it into two equal halves, so return false. If the sum is even, the problem boils down to finding if there's any subset that adds up to exactly half the total sum. We saw that dynamic programming is a great way to solve this subset sum problem. We keep track of all the sums we can make. For each number in the input, we update this record of possible sums. The key trick, if using a Boolean array, is to iterate downwards when updating, to avoid using the same number multiple times inappropriately. Finally, we just check if our target sum, half the total, ever became achievable. Hopefully, that explanation made the partition equal subset sum problem much clearer. If this helped you understand the logic and the DP solution, please hit that like button, consider subscribing for more LeetCode breakdowns, and feel free to drop any questions or thoughts in the comments below. And hey, if you're feeling extra supportive, you can always contribute to the Boba Fund. Thanks for watching, keep practicing, and I'll see you in the next video.